So this talk is going to be really a domain talk about applying artificial intelligence techniques to a particular domain, and and along the way I'll probably give some maybe opinionated comments about AI. So about me, which is why you're here today, right? You all came to hear me talk about myself. Anyway, I'm a data scientist at the IU School of Medicine, and in '93, which is a long time ago, I got my bachelor's in math and English literature at McGill. Then I sort of studied around for a while because I wasn't quite sure what I wanted to do, so I got 3 masters, one in philosophy of science, one in computer science, and one in artificial intelligence. So I guess the MSc in artificial intelligence is why I'm here giving this talk. And Carol, who many of you know, asked me if I'd give this talk because she said, "You're an expert in AI, right?" And I said, "Sure, we'll go with that." I do have a PhD. It's in databases, though. It's not in artificial intelligence. However, my PhD minor was in artificial intelligence. And so for my MSc, I did automated reasoning with Alan Bundy at University of Edinburgh. And for my PhD, my minor, I did case-based reasoning with David Leake at IU. Okay. So here's the domain question. And really, is there an efficient and reliable way to predict whether a building in Detroit, specifically, is blighted from publicly accessible data common to large cities? So why would you want to know something like this? Well, Detroit, as everyone knows, has been faced with a particular problem of blight as people leave their houses, abandon them, and so whole neighborhoods have essentially fallen into disrepair, and people still live in them, and so it's sort of, as a city, you would want to know where to put your resources and what needs fixing. So this is just one of the things. So I did this project for the data science specialization at Coursera, and I did it in 2016. So at the time, this data was fresher. And essentially, we were given certain data for from the specialization. And what we were given is crime incidents for 2015, 311 complaints. Does everyone know what a 311 complaint is? So a 311 complaint is essentially if your neighbors call up and say, "Oh, the grass is never mowed," or, "Oh, they keep, broken down cars in their front yard." And blight violations, these are a bit different than 311 complaints, but they're also similar. And then demolition permits for 2015. So that's really how we are determining whether a building is blighted or not, is if it has a demolition permit scheduled. And so the first thing I wanted to do when I started this project is to visualize the data, because that's often an important first step in figuring out where you're going. So this may not show up that well, especially at the back of the room, but this is using the basemap package in Python. And this is Detroit, the city limits. And the shades of red are crime incidents. So where it's a darker red, there's more crime. And where there's no red, there were no reported incidents. And so Detroit is really, and each city is really broken down into parcels. A parcel is really an address. So it could be a building, it could be an apartment house, it could be a private house, it could be a store. And so some parcels are bigger than others, like this little island in the lake off of Detroit. That's an entire parcel by itself. So these are the 311 complaints. And one thing to note is they don't perfectly overlap with the crime complaints. So it's not necessarily the case that 311 complaints only occurred where there was a lot of crime, or vice versa. And here's the blight violations in blue. And again, darker colors mean that there were more of them. And again, these don't perfectly overlap. So I went out, essentially in visualizing these, it gave me a clue that maybe the data was somewhat incomplete and that parcels could have one or two or all three of these be, say, heavily represented, and maybe it would be blighted, maybe it wouldn't be. So I wondered if there was additional data to be had, and I found this thing, the Motor City Mapping Project. So City of Detroit got a grant, and essentially they sent out a whole bunch of social workers into the city, and these people actually drove around, and with every parcel, they gave a list of their assessment of its situation. So the things they looked at were its overall condition, whether there was dumping on the property, whether it had obviously been burned, whether it had been clearly improved, like maybe a garage built, whether it was maintained, needed boarding, etc. And they also took pictures of all of these buildings, every parcel in Detroit. And so that was very useful data that wasn't given with the course itself that I found. And I also found data on neighborhoods, which are useful because there were something like, I think 30,000, either 30 or 50,000 parcels in Detroit. And if you're trying to, for example, figure out where the closest point is to each parcel, and you have, each point is, say, a crime, and you have 30,000 of those and 30,000 parcels, trying to do that search is, it can get prohibitive. And so neighborhoods are actually useful for narrowing down search, essentially. And here are some examples of houses that were looked at in the Motor City Mapping Project. So the first one, now do I get a mouse? No. The first one over here is A, and that's fair. So you can see that it's missing some glass in its windows. The second one at the top is B, and you can see it's boarded up along the bottom, and it's missing its windows. C is over here at the right, so this is kind of going clockwise, and that's pretty clearly a blighted property. And so they, the Motor City Mapping person who went there gave it a suggest demolition ranking. And then D, this looks like a perfectly reasonable house, and so that condition was considered to be good. So that just gives you an example of the range of blight, from really kind of no blight or very little blight to a lot of blight. Okay, so I'll just go pretty quickly through here the back end because it's a database back end. It's not so Python doesn't come into this yet. Essentially, I threw everything into Postgres, and which tends to be my knee-jerk reaction whenever I have a project is how can I apply a database to this? And that's sort of because that's my hammer, and so everything looks like a nail that I can use SQL to address. So Postgres is great, partly because it's free and open source, and it has a PostGIS extension, a PostGIS extension for geographic information systems. So essentially that enables you to not only have the concept of tables and rows, but you can also have the concept of points and polygons and lines. And a parcel is just a polygon. And a crime incident, for example, has a latitude and longitude, so it's a point. Oh, and here are the numbers. So let's see. There were 200 neighborhoods, and I said there were 30,000 parcels, and I totally misspoke because there's actually almost 400,000 of them, which is the numbers that's a little bit bigger, just a little. And there were 307,000 blight violations, about 20,000 complaints, 311 complaints and about 120,000 crimes in this data that I was given. So these numbers show you a little, they're an order of magnitude more than I said they were, and that probably gives you a better idea of why it is I had to use neighborhoods to narrow down search. So what I wanted to do was figure out, what crimes belong to which buildings, or what 311 complaints, what address were they about, what parcel were they about. So I had parcels on the one hand, and I had all these incidents on the other. And essentially that's mapping points to polygons, which brute force search is fairly impractical. As I already mentioned, I used the neighborhoods. And what I found was that actually, probably owing to differences in, say, the GPS systems maybe that were used to report the crimes, I was off often by something around 20 meters or so. So essentially a point was considered to be in a parcel if it was within 25 meters of it. And I also did some, this is really all data cleaning. And so Alyssa was talking about cleaning your data. And so everything up until this point really has just all been about data cleaning, which is, the boring part. But it's the necessary part. And, I had to get the data into a form where the computer could actually use it before I could do anything. And one thing, another way I approached basically figuring out how the violations mapped to parcels was by address matching, which is not as straightforward as one might think. So there are many different ways of writing down an address. Usually the number's the same, 1, 2, 3, but then, suppose you have St. John. Is that a street? Is it a boulevard? Is it an avenue? And is it St. John ST with a period? Or is it St. John, in all capitals? So it wasn't necessarily clear how things matched. And I essentially had to use some fuzzy matching logic to do this, which helped. And I did it in SQL as opposed to Python. But as I say, that's kind of like my hammer that I use on everything. And it was fairly fast. The nice thing about databases is, if you do a 300,000 by 300,000 matrix in Python, and then you attempt to, fill out every cell, it dies. And on the other hand, in a database, if you do that, it won't die, and it'll eventually complete. So that's one nice thing, is that it did eventually complete. Okay, I think I already mentioned this, but the way we defined blight was if there was a dismantle permit, or if the condition from the Motor City mapping was suggest demolition. And this is where we start getting into what Alyssa was talking about, where we're going to have our data, our features, and then we're going to have our classification. So a building is either blighted or not blighted, and if it's not blighted, it's one of those three conditions. It's either fair, good, or needs boarding, for example. But ultimately, we're interested in blighted versus not blighted, so you can think of it as a binary problem. Using these conditions of either suggest demolition or dismantle, there were about 6,000 of the parcels that were blighted in the data. And in order to have a negative set as well, I chose the same number of ones that weren't actually blighted in the data, so about 6,000, and split this into a 60-20-20 training validation test split. So I should probably have asked at the beginning, but take, for example, training validation test split. How many people are familiar with the training validation test split kind of paradigm? Okay, a few. That's good. Essentially, you need to train your model or your learning algorithm on data. And you also wanted to validate your you want to validate that your classifier has actually learned what you want it to learn. And you use the validation data not only to say yes or no, my algorithm has learned the classification or not. You also can use it to kind of tweak the training, sort of go back and retrain. So training and validation data can be used together, but then you leave your test data off to the side. And when you're completely finished with your algorithm, it's all ready to ship. You're saying, like, this is what I'm going to get my grade on. That's when you test it. And the test data should be completely new data that's of the same type and has the same answers, namely blighted or not blighted, but is completely fresh data. So you don't, of course, if you were using the same data to train your model on that you tested it on, of course it would perform very well. Okay, so finally we're into the AI. And once I had cleaned up the data, got it in a database, put it in a form that I figured I could use, then it was a question of what do I throw at it? So what machine learning techniques do I throw at this? Essentially, I want something that takes in all these features, like how many crimes were in that parcel, how many 311 complaints were there, and I want it to spit out an answer of blighted or not blighted. And I'd like it to do that so that it performs well on my test data or my validation data. So one of the, I essentially used two techniques towards this goal, and one was decision trees and the other one was neural nets. So who's familiar with decision trees? A few people. They're fairly simple. Over here at the right, I have an example, and probably just by seeing the example you can get a good idea of what it is. So this is actually a little decision tree about whether you lived or died on the Titanic. It's a pretty classic example. And let's see, Kaggle, I think it's like the first Kaggle question, right, is to try and machine learn who lived and who died. So at the top, we have a question. Is sex male? Yes, go this way. No, go that way. And you survived with a 73% chance. So basically, if you were female, you had a lot better chance of surviving on the Titanic. And then if you were male, there were other questions. SIB-SP is the number of siblings or spouse. So if you had a large family, you didn't do too well. And if you were an older man, so not a child, you also didn't do too well. And you can tell, basically this is a directed acyclic graph, so all the edges are pointing down. It's got no cycles. It's a tree, which of course, as computer scientists, that's our bread and butter is trees. And its nodes are conditions, its edges are decisions. Okay, so you go yes or no. Essentially, it's an algorithm for classification. And there are different kinds of decision trees. It's actually a very flexible framework. So this one is for classification, which is discrete classes at the end, and the leaves are really the the classes. So died or survived. Those are our classes that we're looking to divide all of our data into. But you can also have decision trees that operate in the continuous field, and then it's called regression instead of classification. And then there's just a bit more. These are a bit more advanced concepts with decision trees. I do want to talk a little bit about the idea of Gini impurity, because I mention it later. And what Gini impurity is really, it's really a measure of how well your condition divides your data. So if it divides your data completely in half, that's not very good, because if you think of it, if it were to divide your data such that there was nobody in this category and everyone was in this category, that would be perfect, because you've classified everybody. On the other hand, if you've divided your data so that there's half in each category, given a new person, you can't really tell which one they're going to go in. Which informally, and that's probably not quite right, but roughly, if a Gini coefficient is lower, that's what you want. And if it's higher, I think its max is 1, but if it's higher, that's what you don't want. So you want sort of discriminatory power in all of these decisions. And here's a decision tree. So this is, I used the scikit-learn package, so just the normal decision trees from there in Python. And this is visualized with matplotlib. There's a plugin for scikit-learn decision trees, which gives you this nice type of graph. And this is purely using the counts, so just using the crime data, the blight violations, the 311 complaints, and the demolition permits. Actually, I didn't use the demolition permits because they're part of the answer, but basically it's just using those 3. And I don't know if people can read this. There is another screen at the back there, but basically at the top here, you're looking at whether the violation count is less than or greater than 0.5. So your Gini's 0.5, which makes it a balanced tree, but it's not particularly, it's probably about as good as it could do. And what to look at really is the leaves and see what happens down here. And by the time we've looked at the leaves, so it splits on the violations, then on the crime count, and again on the violation count, then on the complaints at the 3rd level, and finally on the leaves. That's really kind of as good as it felt it could do for classification. And you'll notice that the Gini scores are all pretty close to 0.5, except there's one there that's 0.2975, and there's another one that's 0. The Gini score is 0 in this little orange category. So if you had a violation count of less than 0.5, a crime count of less than 0.5, a complaint count of less than 2.5, then you were blighted. And it could tell with certainty that you were blighted in that case. All the other ones didn't necessarily split the data as well as you might have liked. So in evaluating the model, I ran it on the test data and basically figured out how many of the test cases were classified properly. And that was the accuracy. So 61% of my test cases were classified properly by this model, which is not super great. There's the notion of precision and recall. Precision is essentially, if I say something is blighted, is it actually blighted? And recall is, if something is blighted, can I find it? So do I actually classify it as blighted? They're kind of two sides of the evaluation coin there. And I don't know if anyone's, who's familiar with these terms, precision and recall? A couple folks. Essentially, they're kind of, they're trade-offs, really. So in machine learning algorithms, you can often get a very high precision, but your recall is terrible. Or you can get a very high recall, but your precision is terrible. And then the F-score is an evaluation function that combines precision and recall and kind of gives you an overall idea of how your algorithm does. And for this model, it was 66%. And you can see that its precision was not so great. So given an example, if it said it was blighted, it wasn't necessarily blighted. And its recall was not too bad. So it actually managed to find a lot of the blighted buildings. It's just that it also found non-blighted buildings and called them blighted, basically. So false negatives, false positives. Yeah, false positives. And so that's the decision tree. I looked at a learning curve. So this is the number of training examples and the error basically in your testing set or your training set. So it's trying to minimize that error. And what you see is in the beginning, so if I only give it a couple examples, of course it doesn't do terribly well, you'll see about 2,000 examples in, everything gets flat. That basically means that the model wasn't really learning anything from additional examples. So I could give it 2,000 examples, or I could give it 5,000, and it didn't really learn anything more from the additional 3,000. And that's a sign, essentially, that you need more features in your data. Okay, so it's a sign that basically blighted is probably not deducible from just the 311 complaints and the crime and the violations. So given those three, which a city usually captures those three, unfortunately they're not particularly good at determining blight. I was kind of surprised that crime wasn't very good, but it wasn't actually that good. So I added some features, which were the motor city mapping data features. So I added things like, at the top here, at the root, for example, it's whether it's unoccupied. So that was a fairly good discriminant in terms of it split the data equally, but yet, as I said, you're going down here where you want to try and get low Gini scores eventually. So splitting like that makes a nice even tree, and it still found, a lot of pretty high Gini scores, and so it couldn't actually discriminate as well as I would have thought from this data. So the accuracy of this, which is just the straight up how many did it get right, is 88%, which is not terrible. That's almost 90%, which is almost an A in the schools where I went. And the precision was a bit lower than the recall, and the F-score was also 88%, just like the accuracy. So the motor city mapping data did buy us something. It's just that it didn't perfectly characterize blightedness, which again, I was a little surprised, that even people driving around and looking at these houses didn't, perfectly capture the notion of blight. The other problem with the motor city mapping data is they had a grant to do this, and they actually sent out a fleet of social workers. But not every city is going to have that money, and not every city is going to have social workers who want to go into all these neighborhoods and take pictures. Oh, I'm just taking a picture of your house to determine if it's blighted. No problem, sir. Put away your shotgun. So it's not always going to be feasible. So wouldn't it be nice if we had something or someone that was driving around in every neighborhood, taking pictures of every single house all over the planet? I wonder if there's anybody who satisfies that. Yes, Google does. So these pictures are actually from Google. And Google has an API where if you send it an address, it will send you back a picture of what's at that address. So we don't have a fleet of social workers, but we do have a fleet of Google cars with their little cameras on top. And so I thought, okay, let's try doing this from images. And these are the same pictures as you saw previously. So as Alyssa was alluding to, there are certain good problems for machine learning and certain bad problems. If you can look at one of these pictures and immediately see, in about a second, that it's blighted or not, that's probably a fairly good machine learning problem. And so, and I want to go beyond that and say it's not really that it's a good machine learning problem, because, can you describe why you can tell this in less than a second? I gave some ideas, like the windows are broken out, and that one's falling down. It looks like it's been burned. but you can't necessarily pick these features. You can tell it's blighted, but you can't necessarily say exactly why you think it's blighted. So that's a good case for learning features along with learning the answer. And that's a particularly good case for neural nets. Essentially, if you don't know what features might be important, throw a neural net at it, because it'll figure it out. So who's familiar with neural nets? More people. So they've gotten quite a bit of hype, and back in the 90s, which is such a long time ago, when I was at Edinburgh, they were also getting a lot of hype. The problem with the 90s is that we did not have the compute power to actually do anything non-trivial with neural nets. So here's an example of one. It's got 3 input nodes, a hidden layer, and an output, 2 output nodes. And if you don't know what a neural net is, there's sort of 2 answers of what is a neural net. One is, it's a function. That's all it is. 2 is, it's an imitation of the structure in your brain. So we have neurons in our brain, and they're all interconnected. And so this is an attempt to recapitulate that structure and use it, apply it to learning. Now, one thing that's up on this slide is backpropagation. So this is a feed-forward neural net. So you'll notice it's actually all the arrows are pointing forward. There aren't any that go backwards. And it's kind of the simplest. They're also called multi-layer perceptrons, but essentially they're all the information flows in one direction, and they have no memory. So nowadays, you're getting into recurrent neural nets, which have arrows going back, which gives them something like memory. I guess I don't want to say terribly much about neural nets, other than, what do I want to say? Well, each node is essentially the input accepts a function, or accepts a value, whatever your input is. So in this case, the input would be images, so it's accepting a huge vector of pixels, basically. So this might be my input. And then your hidden layers essentially each have an activation function in each node, and it takes the input vector, applies the activation function, which often is sigmoid, so it might be, a nice curvy function, or it could be just the function, just the identity function, so pass through whatever you're given, just pass it through. And one function that works quite well, surprisingly well, is a function that's 0 for negative numbers, and then the identity function for positive numbers. That's called ReLU, and it actually works amazingly well. And essentially, those hidden nodes apply the activation function, and then shoot it to the output nodes, and these then would be your classification in our case, say. So in our case, we would probably only have 1 output node. Actually 2. If one fires, it would be blighted, and if the other one fires, it would be non-blighted. Okay. Deep learning. So in a neural net, like the ones that I studied in the 90s, you have like 1 hidden layer, maybe 2 or 3. I should mention overfitting, and that is if you have many hidden layers, you actually do what's called overfit, and that is if you have more combinations of hidden layers and arcs between them, you can actually essentially memorize all of your input data. So if I give it, 10,000 inputs, and there's 10,000 combinations of those nodes plus their their input arrows. So 10,000 connections. It can essentially memorize those 10,000 inputs. And if you give it one of those inputs, it'll be perfect. If you give it something new, it doesn't know what you're talking about, because all it's done is memorize, your 10,000 data points. So one way to get around overfitting is to do what's called regularize, and there are several ways to regularize. One of them, though, is you essentially take kind of your hammer of randomness, and you just smack those nodes every so often. So one might drop out. One might give you different results all of a sudden. So essentially, you can regularize it by not allowing it to use its connections to memorize your data, because you just randomly basically break a node. And so it's forced to actually it's forced to generalize, basically, because it can't count on any particular node. And that's essentially a regularized multi-layer perceptron is called a convolutional neural network, which you might find that name, and it's tossed around, and as if it's very, very abstruse, and completely ununderstandable. But all it is a regularized multi-layer perceptron. So it's one of these things where you randomly drop out nodes at each stage of your learning. And so then there's deep learning, which is the current buzzword. And it turns out that you only really need 2 hidden layers to be classified as deep learning, which is kind of amazing. Doesn't seem particularly deep. Now, usually there are more. And what's interesting is where this has been applied. And so it's been applied to speech recognition, digit recognition, and in particular, image recognition. So there's the cat. Alyssa had a dog, but it's really the same problem. Neural nets have been applied, deep neural nets have been applied to recognizing cats or dogs, which is also a Kaggle competition. So here we go. In October 2012, a couple students of Jeff Hinton, who's a big AI person, won ImageNet. So what ImageNet is it's like millions of images, and you want to classify them and say what is in them. And so 2 of his students actually won this. They came up with a machine learning program that was able to, with I think around over 90% accuracy, tell what was in these images. Like, this one's a house, this one's a barn, this one's a road, this one's a traffic light, this one's a cat, which is amazing. And there's a great Fortune article, a Fortune.com article on that. And, everybody said, oh, image recognition is solved. No problem. It kind of maybe is, maybe it's not. So one problem is, they threw a lot of resources into training their system. So if you're Google, I believe that you can train an image recognition neural net that will basically work. But, you have Google Cloud. You can buy whatever resources you need if Google Cloud isn't big enough. And you can run it for 6 months, because you can afford it. You can run it for 6 months on, 84 cores, 1,600 of them, all churning away. So you can compute those millions and millions of images with their answers, and you can come up with something that has learned that pretty well. Now, if you're me and you're doing this Coursera project, you don't have access to an awful lot of resources. For starters, I think the deadline was like 6 weeks, which is not a lot of time to train a neural net, especially a deep one. So I cheated. I used what's called transfer learning, and essentially what I took was exception, which is a deep neural net that had been trained on ImageNet and already knew ImageNet. And so exception, XCEPTION, it was written by the Keras guys. So who's familiar with Keras? Okay, a few. It's the Python front end, essentially, to TensorFlow, which is the neural net, or really more generally a graph sort of simulation. And so exception is pretty heavy duty, and it essentially knows ImageNet. And all I did was slap on a classifier on the front. Now, my classifier happened to be also a neural net, but I could have chosen anything like a decision tree to stick on the front of it. So I have exception here, this sort of really heavy-duty image recognizer that's going to pick out some features of my houses, my pictures of houses, and it's going to feed them into my classifier. And my classifier is going to learn how to map the results of exception to blighted or not blighted. So how did it do? That's the main question. It took 5 hours to train. Its accuracy was 84. Wow. I have these up there just because I was like reminded of accessibility by the previous talk, and this looks really terrible. I mean, honestly, they're translating this and it's total gibberish. Seriously, these are the closed captions for this being automatically generated. Okay, I apologize to the folks who want to actually use these closed caption. I should probably just turn them off if I can. Okay, there we go. They're gone. They obviously need a better neural net. So it took 5 hours. Its accuracy was 84%. So not as good as the Motor City mapping data, but better than the violations. Here's some numbers that it assigned. So a higher number means better condition, pretty much. So it was really certain that that's blighted, this one over here on the right, which I thought was interesting. I didn't stop there because I wasn't super happy with 84%, so I put together the counts, I put together the Motor City mapping data and the neural net. And so essentially there was only one feature from the Motor City mapping that was important, and that was whether it was unoccupied. And if it was unoccupied, then my image mapper could do really well and tell the difference between blighted and not blighted. So this accuracy was 94%, and the F-score the same, which is, fairly decent. I think exception got something like 98% on ImageNet, so it's a pretty good recognizer. Here's a summary. I also tried VGG16, which is another contender for the ImageNet prizes, because they give prizes if you can get the ImageNet correctly classified. And VGG16 did not do as well. Then there's some links. And I guess I should also mention Wikipedia, because of course, where do you go? You go to Wikipedia. So I can highly recommend Wikipedia if you want to learn about decision trees and neural nets. And anyway, there we go. That's it. Okay. What Postgres features would you recommend looking into for aspiring data scientists? I think it's not so much Postgres as the relational model, and in particular SQL, so structured query language. So the relational model, which is basically tables and operations on tables, really, if you know that, then I'd say you can do, 90% of data science, pretty much. At least that's what I find. So SQL is really still a very powerful data manipulation and querying language. So learn SQL.
All right. Any other questions for Cathy? All right. Let me bring this around.
Hey, Cathy.
Hi.
So for beginner data scientists, can you think of any hello world data sets that could be relevant to learn more about neural networks?
Sure. So there's a couple. One is Kaggle, of course. because they're big. Another is UCI, so University of, is it California at Irving, I think, has machine learning data sets. So for example, they have the data from these kind of watches, so the accelerometer data, and then a task is to classify it into, whether I'm standing or sitting or running or walking, and it actually works, and so there's examples, there's lots of data, and there's actual problems that are tractable, which is what you want. You want tractable data when you're first starting out. You don't want someone to throw, genetic data at you, which is usually terribly dirty, horribly huge, and so you want these nice sort of a little bit curated data sets. So Kaggle and UCI.
Does that same advice fall true for like the iris data?
Oh, the iris data is also good. Yeah,
Okay.
that's the it's also good. It's where is iris at again? I forget. But iris is basically a whole bunch of flower data. So there's classifying flowers basically. So based on its petals and its stamen and its whatever else flowers have that I don't even know about. But yeah, that's another good one.
All right. You bring-
Thank you, Cathy. I just want to ask, so you got the images from Google
Right.
API? How many are those images? that
How,
you're-
how many images?
Yeah. that
So
you're-
I used, actually, you can put in any address you want and get it back, but I think I used about 5,000. Actually, did I even say that?
Okay, I must have missed it if you put it there. 5,000 images.
I think I used, the 6,000 that I had and split like 60, 20, 20.
Okay.
So I used that same data set. So I didn't need nearly as much data to train my little classifier. If I'd
Okay.
wanted to train exception, I would have needed,
Oh.
millions of images.
Oh, because you're using a transfer learning already.
Right,
Is that
right.
the reason? Okay.
Right.
Okay, cool. All right, thank you.
Sure.
Any other questions for Cathy?
Thank you, Cathy. I had kind of two questions, and if you don't want to say, or if you'd rather give other people in the room the opportunity to answer, that's great as well. One of the questions is if there was any particular part of this that you felt to be intellectual property. Imagine you were doing this, in a commercial venture. Which part of this would you not be willing to talk about with people that were asking you, how did you do this? And that's partly coming from the point of view of if you were a client and you wanted to lift the lid on the black box, how would you talk about that? Would you give them a presentation like this with all of that detail? Or is there things that you would want to keep under wraps? And I found it fascinating. The other question is, can we have a word afterwards? Because it's been brilliant. Thank you.
Sure. Let's see. So,
Sounds
this
like Paul's got something he wants to hide and he wants to know how much to give up.
So this is actually on GitHub. It's in a repository with all my code and everything I used. So I'm a big open source person, or at least I was before I started working for IU School of Medicine, where now certain things are indeed proprietary. I'd say this talk was at a level where it wouldn't be necessarily trivial to reproduce everything. Certainly giving my GitHub repository, it would be. But it was at a fairly high level still. And it is kind of an issue. So this is a talk that I gave before at the data science group to practice, and I also gave it as a job talk for what I'd been doing with myself, and I had the advantage of not working for anyone at the time except myself. Exception, for example, is fairly black box. Now you can get the exception architecture online, but I think what's nice about exception from the point of view of keeping it proprietary is, you can have the architecture, You can even have all the input data, but unless you're a fairly big organization, you can't actually reproduce the results. So, so that kind of tends to keep a lot of deep neural net stuff as a black box. And as a slightly orthogonal comment, neural nets are kind of black boxes. Inputs go in and outputs come out, and no one's really 100% sure what happens in there. So features get extracted, and every time you have a convolution layer, maybe it's like, for an image, maybe it's like reducing the resolution, maybe? Who knows? They suspect that with facial recognition, there may be a little area of the neural net that learns eyes. But maybe it's just learning that, everyone with brown hair is named Fred. So they are kind of just black boxes. I don't know if that answered your question, but...
We have a question up on the screen.
Oh, is classical AI dead and worth learning? Ooh, I have such an opinion about this. Absolutely not. There have been advances in... So my area, when I went to Edinburgh, was natural language processing. And there have been advances in natural language processing where I'm fairly impressed. Now, in Edinburgh, what I used to say is something like, we don't understand the human brain. We don't understand neural nets. Therefore, they must be the same thing. And that was my way of dismissing neural nets, because I was a classicist, and I did automated reasoning, case-based reasoning. My thesis was on solving GRE problems in a computer. So learning how to solve GRE problems, graduate record exam problems. And so NLP has made great strides. We have these boxes sitting in our homes that we talk to, and they sort of figure out what we're saying and kind of do things okay. And that's quite impressive to me. Like Alexa and Siri and Google. There she is, in fact. Hi, Siri. They're fairly impressive. But there's an awful lot they can't do. And I would say, I always like to ask this question when I was studying AI. Suppose I had a huge multivariate differential equation, and I wrote it down on 120 pages, yes, and that's what I figured. And suppose I had this differential equation, I wrote it down 120 pages, and it perfectly imitated Cathy. Like, it's me. Now you change one coefficient, it's garbage. Okay, and here it is, 120 pages of math. So have I solved AI? What do you think? I mean, if I have this huge differential equation that perfectly imitates Cathy, it does, you put any input into it that you would put into me, and you get the same result. But as I say, you tweak one little number, and it's garbage. So I'm not sure that you've solved AI in that case. Right. Yeah, he's saying you tweak 1% of our DNA and we become apes. So yeah, it's I don't know. I mean, maybe I have solved AI if I had that differential equation. Could have copies of it everywhere, and they would do everything I would do, which is, But yeah, so I think there's always going to be a need for, certainly for explanation, which usually has to be discrete, because we understand concepts, but we don't necessarily understand huge differential equations. And I would even hazard to say that until there's a coherent theory of semantics, they're not going to really solve NLP. Because basically what's happening is they're solving the syntax of NLP. So neural nets are extremely good at learning language syntactically. right? And you have the Tarski truth definition, which is like a sentence basically is what it stands for. So they're very good at doing that, but they're not so good at, you know, human interaction or basically anything in the real world, you know, like grass is green. Sure, it can know grass is green, but maybe that's not really green. Maybe it's kind of yellow, you know. Anyway, sorry, I could go on and on forever. But my feeling is, yes, you need to learn classic techniques, as well as SQL.
All right. Well, I want to thank you, Cathy, for coming and being with us tonight at our La Femme Pythonista event. Let's give her a big round of applause for coming out and speaking and being our Pro Talk speaker.